Okay, so we are recording now, and I'm gonna try to share my screen. I think this is the screen I wanna share. Great. Okay, and I'm just gonna lecture for a little bit. Please, please, please feel free to interrupt at any time to ask questions, to engage in conversation here. So this is me, like, sort of talking through this, but I don't necessarily need this to be a silent lecture. I welcome any comments that you all might have or any questions that you all might have. Okay, so chapter 7 is all about connected sets and what it means for a set to be connected. And when I talk about sets, right, what I'm talking about sets, I'm really thinking about a subset of the real number line, right? Just because everything we do in this class is a subset of the real number line. So if this is my real number line, I'm thinking of connected in a very intuitive way, right? Where a set like this is connected, where I include everything in there. That's a connected set. But if I attached this new piece like this, right, and my set sort of looked like this, the total expression, I would call that a disconnected set. That is a set that in total is not connected, right? So in a certain sense, connectedness is describing something kind of intuitive where we expect intervals to be connected and just about every other kind of set to be disconnected, or anything that's disjoint to be disconnected. But it's actually kind of hard to rigorously define what connected means. And so we actually go about rigorously defining the idea of a connected set in this very roundabout way. We'll ultimately define a set to be connected if it is not disconnected. Yeah, so a set will be connected if it fails to be disconnected. But the actual starting point here is with a set, when we say that a set is separated. So we are going to describe two sets in the real numbers, right? So A and B in the real numbers are called separated sets if and only if the following holds true. The closure of A intersect B, right? So the closure of A was A union the accumulation points of A, right? So closure of A intersect B and A intersect the closure of B are both equal to the empty set. So if we are given two sets A and B, we can check whether this is empty and we can check whether this is empty. And if they are both empty, then we would say that A and B are separated sets. Now, to make meaning out of this definition, we have two examples. We can consider, and this is, I'm just following along with the book, this is exercise 7.2 and exercise 7.3. So for exercise 7.2, we have the closed interval 0 to 1. That's going to be our A. And we have the sort of half open set from 1 to 3. And that's going to be our B. So the question is, are these two sets A and B separated? And the answer is, well, let's find out, right? So in order to determine this, we would have to check the closure of A intersect B, right? And the closure of A, well, A is already a closed set, so it's just going to be 0 to 1, intersect B, that's 1 to 3, right? But since the second set does not include the number 1, this, in fact, is equal to the empty set. So the closure of A intersect B is equal to the empty set. There is no point that is in both of them because this only goes up to 1 and this starts just north of 1. Okay, at the same time though, let's check A intersect the closure of B, right? Well, A, that was the set 0 to 1. And the closure of B, that's going to be the closure of this half open interval, 1 to 3, right? And that is just going to be the closed interval, 1 to 3. right? So the closure of the half open interval 1 to 3 is the fully closed interval 1 to 3. And so A intersect the closure of B is the intersection of those two. And we notice that actually has some intersection. This has the point 1 and this has the point 1. So in particular, this intersection includes just the single element 1, but it is not the empty set. So according to this definition, these two sets would be separated if and only if both of these intersections were equal to the empty set. And since that's not true in this case, we would have to say, sort of collectively, the two sets A and B are not separated. Oops, separated. All right, and that goes sort of, I mean, that's sort of intuitive, or rather that aligns with our sort of picture in our head of these two sets. If I were to draw set A, right, and that's, let's say, from 0 to 1, that's my set A. And then if I were to draw B, that's the open interval, open interval from 1 to 3, right? Then taken together, these two sets butt up against each other, right? The first set includes the number 1. The second set includes everything up to or down to the number 1. So even though it didn't include 1 itself, when we take their union, they end up forming this sort of continuous, connected segment. And so they're not separated from each other. So in a way, separated sets are even stronger, or it's a stronger assumption than disjointed sets, right? A and B here were disjoint. They didn't have any elements in common. And yet, they were not separated. They were still sort of butted up next to each other. Okay, so that was example 1. Example 2, right? Example 2, which is exercise 7.3, is to consider the sets 0 to 1, but let that be open, and 1, 3. Right, so that's going to be our A and our B. And notice this time, neither set contains the number 1 in it. And indeed, if we calculate, again, the closure of A intersect B, once again, this will be 0 to 1 closed, intersect half open, 1 to 3. And so that will be empty. At the same time, A intersect the closure of B. Well, this time, it's not going to have this number 1 in it, right? A no longer has the number 1. And so this set is also the empty set, because this time, there is no element that appears in both of these. The number 1 is no longer in the set A. So in this picture, we actually have that these two sets, A and B, are not only disjoint, they are separated. And if we were to draw the picture that we get as a result, we can see it looks almost the same as the picture above. It just so happens that our set A goes from 0 to 1. Our set B goes from 1 to 3. And we actually notice that there is this teeny tiny little speck of separation between the two, exactly at the point, this point here, at the point x equals 1. So there's that tiny little bit of separation. Okay, so how's everybody feeling about that? I'm going to keep forging ahead, but I'm happy to pause and answer any questions here. And I'll keep an eye on the, excellent. I'll keep an eye on the chat in case anybody ends up typing anything into chat. Okay, so any two sets that you look at, any two sets A and B, you can check to see if they are separated or not separated. Now we get into something a little bit more challenging. A set S is called disconnected if and only if S can be written as the union of two non-empty separated sets. All right, so now I'm talking about a single set S, and it is disconnected if and only if it can be written as the union of two non-empty separated sets. So our go-to example here is going to come from our previous work. So example, consider the set 0 to 1 union. Actually, I'm going to write it in a slightly different way. Consider the set 0 to 3, but take away the element 1. So this is the entire interval from 0 to 3, but I am just removing the interval, removing the single number 1 from it. So we end up with something like this. Right, so it's going to be every single point in there except for, really it should be down here, the point 1. So everything up to 1 and everything after 1, but we have clipped out or we have removed specifically the point 1. This set is a disconnected set. And it's disconnected because according to the definition, it can be written as the union of two non-empty separated sets, right? And to be crystal clear, I can define this set as my set A, this set as my set B. And so specifically, I can say A equals 0 to 1, not including the number 1. B equals 1 to 3, not including the number 1. We can notice that this entire set is equal to A union B, right? So this entire set is the union of two different non-empty and separated sets. These are non-empty because, you know, they each have elements in them, and they're separated from our work up here. So this example can be written as the union of two non-empty separated sets. Okay, so here is a question. Based on our work above, I'll draw sort of a line here. Based on our work above, can we conclude that the total interval 0 to 3 is connected or is not disconnected? Yes, okay. Can we conclude that 0 to 3 is not disconnected? Up here, we had an example of an A and a B. Their union was the entire interval 0 to 3, but we noticed that these two sets themselves were not separated. Right, so can we conclude that 0 to 3 is not disconnected? It's actually kind of a weird and a hard statement, but the truth is that no, we cannot, based on this work alone, conclude that 0 to 3 is not disconnected. And the key sort of idea here, well, a key idea here is this statement, the idea that S can be written as the union of two non-empty separated sets. Right, so in the example above, we said A equals 0 to 1, B equals 1 to 3. Those two sets are not separated, so that does not work. But we cannot conclude, just based on what we've done so far, we cannot conclude that we couldn't dig deep and find some new choice of A and B that happened to work. Does that make sense? In other words, to maybe say it a little more straightforwardly, we have shown that this choice of A and B are not a good choice for this definition, but that doesn't mean that I couldn't find a better choice of A and B, right? Like I could keep trying and I could find maybe a choice A and a choice B that would work in this setting. Okay, let me pause there. So is that, does that make sense? So we have explicitly shown that the second example forms a disconnected set, but we have not explicitly shown that this example forms a disconnected set. And at the moment, we cannot draw a conclusion about the set 0 to 3, that closed interval from 0 to 3. We don't know if it's connected or disconnected. We kind of hope it's connected because that gels with our intuition of what it means to be a connected set, but we cannot conclude it based on the definition. Okay, again, taking silence to mean you're all feeling all right about this. So let's jump to this definition here. So this is just a repeat of the definition on the previous slide. A set S is disconnected if and only if it can be written as the union of two non-empty separated sets. Finally, we get to the definition of connected, which I think is just such a funny definition. A set S is called connected if and only if it is not disconnected. So we sort of define connectedness as a negative. It's not disconnected. And our main theorem in this early part of chapter 7 is this. It says, if S is connected, and if the points A and B are in S, then any point in between A and B must also be in S. In other words, if S is connected, then S must be an interval of some sort, in which if I have 2 points A and B, and they're both in S, everything in between the two will have to be in S as well. Okay, so that is our big theorem, and we have to try to prove it. Let's go ahead and try to give this a go. So proof. Let's see. So we're going to start with our assumptions. We're going to assume that we have 2 points, A and B, and they are in S. Okay, and our strategy for this proof is going to go as follows. We are going to prove this by contradiction, right? So suppose there is an element C in between A and B, with C not an element of S. Right, so our proof is by contradiction. Suppose that there is an element C that is not in S. We are going to turn around and show that S must be disconnected, and that will be our contradiction. So because then it cannot be both connected and disconnected at the same time. So to show that a set is disconnected, I need to show that it can be written as the union of two non-empty separated sets. So this will be my contradiction. I will show that S can be written as the union of two non-empty separated sets, A and B. Okay, and so to do that, I need to find two candidate sets, A and B, with A union B equaling S, with A and B separated, and with neither A nor B being equal to the empty set. Right, so those are the 4 criteria that I need to find here. If I can do that, then I can say that S is separated. And here are going to be my candidates. And to help illustrate this, I'll sketch a quick picture over here on the right. So here's my number line. Here is my point C. Here's my point B and A. All right, so I'm not going to make a claim as to precisely what S is at the moment, but I'm going to say that S, I'll draw my S in red. I know that S contains the number A, I know that S contains the number B, and I know that S does not contain the number C, so C is not red. Then, S might have some number of elements all down here. S might have some number of elements all up here. I don't really know. But I'm going to divide this into two sets, A and B, as follows. I'm going to let capital A, my set capital A, be every element of S that is to the left of C, that is smaller than C. And I'm going to let B, capital B, set B, be everything up here. And I'm going to claim that if I define that correctly, so I'll do that now. I'll say let A equal the original set S intersect the set of all points, set of all X in R, such that X is less than C. All right, and similarly, I will let B be S intersect the set of all points X in R, such that X is greater than C. Right, so my set A, it's not everything to the left of C, it's just those elements of A that are to the left of C. So it's really these points up here. And similarly with B, it's going to be the points of S that are to the right of C. And so I'm going to claim that neither A nor B, capital A nor capital B, is non-empty. I'm sorry, neither one is empty. Both are non-empty. I'm going to claim that A union B is equal to S, and I'm going to show that A and B are separated. So let's dive into it. So first, A is non-empty. Well, how do you show that something is non-empty? You show that it has at least one point in it. And oh, we know that this has at least one point in it because I know that it at least contains the number A, right? I know that A is an element of S, and I know that A is less than C. So because of that, A must be in my set capital A. Right? It might have other points in it too, right? The way I've sort of drawn it, it has all these other points in there as well, but it at least has that one point, and so it definitely is not empty. Similarly, we know that B is non-empty since lowercase b is in capital B. Same reason. Element B is to the right of C, and it is definitely in S. So A is not empty, B is not empty. A union B must equal S, because A union B, right? And let's think through this. We had S intersect the points less than C, union S intersect the points bigger than C. That means we end up with all elements of S except for possibly the point C. But C was not an element of S to begin with, right? So A union B is all of these points, union all of these points. The only point that we might have missed is C, but C was not an element of S by assumption. So A union B equals S. All right, and finally, we have to show that A and B are separated. And to do that, we have to figure out what the closure of A is. Actually, I lied. I don't think we explicitly need to figure that out. Instead, I think that it is sufficient for us to figure out that the closure of A cannot contain any points above C. And if we believe that, right, if we believe that the closure of A is stuck over here, and we know that B only contains elements bigger than C, then we will definitively know that closure of A intersect B is empty, right? Closure of A stuck over here while B is stuck over here. So why is it that the closure of A cannot contain any points above C? Right, it's a good question. So if the closure of A, well, we know that A doesn't contain anything above C, right? We know that A is sort of stuck down here. So if we happen to have some element of the closure, it would have to be an accumulation point, right? And if there was an accumulation point of A floating strictly above C, that would mean if we zoom way in, there would have to be elements of A that were really, really close to it. So there would have to be elements of A, there would have to be elements of A that were above C as well. Right, so if there was an element of the closure of A that was bigger than C, there would have to be elements of A itself that were bigger than C. And by our construction of what A is, that would be impossible. So we know that the closure of A intersect B is non-empty. Is empty. If you're not satisfied with that argument, that was a little hand wavy. It was sort of a proof by picture. We can make this rigorous using the order limit theorem from way back in chapter 4. Right, so the order limit theorem was the one that basically said, do I want to go down this rabbit hole? Of course, I always do. The order limit theorem. The order limit theorem for sequences was the one that said if you have a sequence that is always containing positive values, so if your a sub n is always positive number, then the limit it converges to must also be non-negative, right? So if a sub n is actually, if it's bigger than or equal to 0, then its limit a must also be bigger than or equal to 0. The same thing is in effect here. If our set is less than or equal to C, then any accumulation point must also be less than or equal to C. Okay, rabbit hole done. Similarly, since the closure of A cannot contain, or since the closure of A intersect B is empty, we have a similar argument, which I won't spend too much time talking about, but a similar argument shows that A intersect the closure of B is empty, right? The closure of B necessarily sits above or equal to C, while A continues to sit below C. So our two sets, set A and set B, are separated. And so we have successfully divided our original set S into these two different pieces. So therefore, S is separated. I've sort of run out of room down here, but I'll try to write it tiny, the bottom of the board. So S is separated. But that's a contradiction because we assumed that S was, I'm sorry, I should say, so S is, let's use our language precisely. A and B are separated. S is disconnected. It has been written as the union of two non-empty separated sets. So S is disconnected. And that's problematic because we were supposed to show, or we were assuming initially that S was connected. So contradiction. Okay, awesome. And that's great. What a fun proof. So in short, right, if A is an element of our set and B is an element of our set, every single point between the two must be an element of our set in order for our set to be connected. Otherwise, if even one element in there is not, I can use that element, that non-element, as a wedge to divide my set into two separated pieces. Love it. Any questions about that? Perfect. Okay. Let's see what we've got coming up. We've got a few minutes left. I don't want to keep you late, but I also want to talk more. Let's see. So, let's go ahead and prove. Let's see if we can do this quickly. Let's try to prove theorem 7.7. So what we just proved, let's clarify the difference between this theorem and the previous one. The previous theorem said that if we had a connected set, then that connected set was an interval, which is great. But we haven't explicitly shown that every interval is actually connected. In other words, the issue from the beginning of this lecture, right, the 0 to 3 interval, we still haven't rigorously shown that that is connected. So 7.7 proves this, right? It proves that converse statement. So connected sets are intervals, right? Or a set is an interval if and only if it is connected. Or a set is connected if and only if it's an interval. Great. So let's try to prove that. So we will try to prove this by contradiction. And so to prove this by contradiction, let's take I to be an interval. Let I be an interval. Yikes. Okay, so we've got our interval I. Let's assume that it is disconnected. All right, so this will be another proof by contradiction. Assume I is disconnected, which means by our definition of disconnected, it can be written as the union of two non-empty separated sets A and B. Perfect. So as let I be an interval, assume for contradiction that it is disconnected, i.e. that an interval, our interval can be written as two separated sets, A and B. Okay. I am going to, because these sets are non-empty, I know that there exist elements in each of them. So I'm going to say let little a be an element of big A, and let little b, be an element of big B. And without loss of generality, I'm just going to assume that A is less than B, right? Just to give me a sense of order here. So I have some sort of number line. I have some interval I on this number line, which I'm not really going to specify. But I do know that my set can be divided up into two different separated sets. I've got A, in which there is little a, and I've got B, in which there is little b. Okay, and then what I'm really going to be interested in, and what will really drive this contradiction, is what's happening here in the middle. And so there will be some contradiction that we can draw here. To do that, I have to find a point somewhere in the middle that will cause a contradiction. And I'm going to use the language of the least upper bound, right? The supremum to do to find this point. So specifically, I am going to define a number C, which will be my sort of breaking point, the point that will break this. Let C be defined as the supremum of the following set. The set of all x values that are in A such that x is less than B. Okay, so by the ordering, I've got, my set A, and there's nothing that says my set capital A and set capital B have to themselves be connected, right? Like maybe all of my blue color here represents set B, all of my red color represents set A. But what I'll end up getting is I'll get a supremum. This is actually over here. right? I can take my set A, I can take the least upper bound of all of my points A that are less than B, and I can call that supremum C. So that's sort of happening right there. To be guaranteed that the supremum exists, I need to know that this set I'm looking at is bounded above, right? So this set, I guess this set right here is bounded above. Specifically, it's bounded above by lowercase b, right? Whatever that set is, it's definitely bounded above by lowercase b. So the axiom of completeness guarantees that it has a least upper bound. So it guarantees that the supremum, aka C, exists. Okay, so I'm going to claim that C must be less than or equal to B, true by how we've defined this. It is also the case that C must be greater than or equal to little a, right? That's because A is an element of this set. And so the supremum of the set must be bigger than or equal to every element in the set. So we definitely know that C is in between little a and little b. So the sort of intuitive picture that I've drawn here at least kind of makes sense. C is between a and b. And so we want to make now a contradiction to the fact that A is disconnected, or rather that the sets A and B are separated. And it looks like I'm going to run out of time. So I'll say here, to be shown. Right? C causes a contradiction. And I'll even hint at what the contradiction is. C causes a contradiction. And the contradiction will be that either the closure of A intersect B, or the closure of B intersect A must contain C. Right? And we can sort of see that, I mean, not rigorously, but we can guess that that's probably the case by looking at this picture, right? It's the C is describing a specific point where set capital A and set capital B are kind of meeting, and that will be a problem for the idea of A and B being separated from each other. All right, so I don't want to keep anybody after, so I guess we are basically just about out of time. I'll end just by telling you quickly what I see us doing next week, right? So chapter 7 is a fun chapter, but it's a chapter that just sort of, it's a relatively short chapter, I guess. It tries to prove a point relatively quickly. It focuses on this intermediate value theorem and this idea of connectedness. And we're already, just in the short time that we've been talking, more than halfway done with the chapter. So what I'm actually going to do is I'm going to sort of soar over most of this chapter in the sense that I don't think we're going to spend much class time on chapter 7. I will create a couple more videos sort of talking through these next few theorems and ask you to read them, and there will be some questions that we can discuss about them. But starting next week, I think our big meaty chapter that we're going to jump into will actually be chapter 8. And chapter 8 is where we will pick up this idea of open covers again. Open covers were things that we looked at briefly back in chapter 3. They were a little confusing. They are confusing, and they were confusing then, but they set the stage, or sort of introducing them back then was to set the stage for what's to come in chapter 8. So just know that over the next few days, I'll create some videos, I'll post them on YouTube in which we talk through the rest of chapter 7. And we talk through a little bit of chapter 8. And the preliminary stuff that I'll ask you to do for Monday's class down the road will focus on some of the preliminary work in chapter 8 as we get into this really challenging but really meaningful conversation of what makes a compact set. So I think it should be a lot of fun. That's what we have to look forward to. In the meantime, though, you have homework due on Thursday/Friday/Saturday at 8 a.m. So don't forget about that. I will post this recording to the YouTube channel so you can rewatch some of this early chapter 7 stuff.